computer. Okay, now I'm recording. Sorry, I got through most of section 1 without recording. We talked about vectors a little bit. Talked about motion in east and west and north and south, and adding those together using Pythagorean theorem and so on. But if you need a review on that, please watch one of my other videos on chapter 3. I pretty much cover it the same way all the time. But anyway, we're at this point now where we're talking about this independence of motion. If you drop a ball and throw a ball forward, there is this independence of motion that's at 90 degrees to each other. And one of my favorite ways to talk about this, particularly in Nebraska, where a lot of people have experience hunting or shooting guns, is shooting guns. It's often shown in the movies. You've probably seen a movie before where somebody shoots a gun, and then a couple of seconds later, something gets hit by the gun, or someone gets hit by the bullet or something like this. But that's not very realistic, actually. Anybody who's been to a gun range knows that that's not realistic. Even if you point the gun up, it doesn't stay in the air for very long. So the question that I often like to ask is, if you have a gun that is shooting straight horizontal to the ground, guns are not designed to do that technically. They're designed with their sights to shoot up a little bit, just because of trajectory of motion and everything. But if you did actually have a rifle that you were shooting perfectly level to the ground, and you pulled the trigger and shot the gun, how long would the bullet stay in the air? And I usually give my students, 3 options. Would it be 1 second, 5 seconds, or 10 seconds, right? And how do you answer that question? Can you do an experiment to estimate how long a bullet would stay in the air? And the experiment's kind of right in front of you, isn't it? Because a dropped bullet would stay in the air the same amount of time if this principle is true. It doesn't matter that the bullet's moving super fast straight forward. A lot of people think, well, the bullet is spinning, so doesn't that keep it in the air longer? Nope, doesn't. All that spinning does is makes the bullet go straight. That's the only thing it does. It doesn't do anything to the trajectory of the bullet. Well, it does prevent it from getting tilted off course a little bit so it doesn't wobble around in the air. But the overall trajectory of the bullet, it doesn't affect it. It doesn't make it go up or down or stay up longer. So the experiment is, drop something. So I've got, and it doesn't even matter what the thing is. It can be about the weight of a bullet or not. It doesn't matter, it turns out. But if you just drop something, you find out it's about a second, a little bit less than a second, actually. Right? It's a simple experiment. And that's how long a bullet stays in the air if it hits nothing, if it hits nothing before it hits the ground, right? The only thing that is, the only caveat to that is that if the bullet starts going extremely fast, if it goes like way faster than a bullet has ever gone, okay, faster than Superman even, right? Since he's faster than a speeding bullet. Then when you fall, when the bullet starts to fall, it actually starts to fall over the edge of the horizon. It essentially falls off the edge of the earth, right? And since we know the edge of the earth is actually not the edge of the earth, it's just the curvature of the earth, then if you're going fast enough, you can actually fall around the curvature of the earth. And we call that being in orbit, right? It's extremely difficult to go that fast. With a bullet, it can't be done with a bullet. It can't even be done with a jet plane. We tried that for many years, and rocket planes we tried it with. Eventually they got it done with a huge rocket. They eventually got somebody into orbit with a very large rocket, and Alan Shepard was shot into orbit. He orbited the Earth almost once, I think, not quite once. But he wasn't the first. It was actually Yuri Gagarin of Russia. He was the USSR at the time, but he was Russian. And Yuri Gagarin was the first one to go into space by being shot sideways with a rocket fast enough that every time he fell, he just fell around the Earth, right? He just fell in around the curvature of the Earth, which is what we call being in orbit. This great cartoon that I used to read as a kid called the Wizard of Id. Have you ever heard of that one? It was about this. No, wait, it wasn't. No, it wasn't. It was called BC. Now that I'm thinking about it, I used to read both of those. But BC was about a caveman, a group of cavemen, and it was just goofy things about these cavemen. But there was this one kind of hairy caveman who was supposed to be like, the missing link or whatever. And he was playing golf one day with his rock tied to a stick, and he was hitting another rock as his golf ball. And he was supposedly super strong, so he hit the golf ball, and it went zooming off the screen, and then next time it came back through the other screen this way. He hit a golf ball into orbit. He hit it so fast. Be very, very, very fast ball. You wouldn't even see it fly by. Anyway, the point here is that these motions are very independent of each other because of their 90 degree to each other kind of relationship, right? If you're moving horizontally, you are not moving vertically, therefore you will not be affecting that vertical motion with your horizontal motion. Here they have a nice demonstration. You want to get into a simulation. I thought they'd gotten rid of all the Java simulations, but apparently they hadn't quite. Thought they'd moved them all into HTML5. But anyway, you can move this ladybug, and you can actually see vectors. So you're essentially giving it some acceleration and some velocity, and it shows the vectors. Right? So here it has a velocity vector and an acceleration vector. The velocity vector is going to be to the right, and the acceleration vector will be to the right, but then it'll slow down. And that's because it's going to need a deceleration to slow down, or an acceleration in the opposite direction. And you can also do different kinds of motion automatically, like this. You can do a circular motion. Circular motion is interesting because the velocity and the acceleration are perpendicular to each other. We'll learn more about that. Elliptical motion, which is more realistic for like planets and things, where the acceleration is changing all the time. Even the velocity changes a bit. Well, this is actually a constant velocity one now. I'm looking at it. But anyway, just gives you an idea of some vectors in 2 dimensions, how they can change and rotate and other things. I actually find that one more useful when we get into circular motion. But anyway. Here we have a nice map of Hawaii, the big island of Hawaii. We have Maui, Molokai, Lanai, right? So anybody been to Hawaii? Yeah, you ever been to the big island, Hawaii? Yeah, that's my favorite island with the volcano on it. It's like it's a baby continent. It's a continent being born. It's been, in its infanthood for a million years. Anyway, no, maybe not quite that long, but quite a while. Here we have a trip that somebody's going to take in a plane or a boat or something, and it looks like a plane because they're going right over the top of Maui. But they take this trip here. They have several different stops, and each one of these could be considered a different displacement vector for each part of the trip. But the overall displacement, of course, would be the dotted line from where they started to where they ended, right? And if we did the math of this, here they talk about that head-to-tail method of adding vectors together. We have one displacement in the east and west, one displacement in the north and south. Then the 2 displacements added together are the head. You go from the tail of the first one to the head of the second one after you've put the first 2 vectors you're adding together in head-to-tail configuration. But you can do this for a lot more complex ones too. So down here, they do this for a lot more complex system where we have 3 vectors that are not necessarily pointing just east and west or north and south or just in the X, just in the Y. This one's pointing off at 49 degrees. This one's pointing off at 15 degrees, all measured from the X-axis. This one's pointing off at negative 68 degrees from the X-axis. And if you put these all head to tail, 3 in a row, they look like this, boom, boom, boom. And then your overall displacement starts here and goes to there. So looks like that. And you can calculate what the length of that is using geometry, some trigonometry if you want. But it's a pain in the neck. You could also just carefully draw this picture perfectly right with all the perfect angles, the perfect lengths on, you know, graph paper like you did in whatever grade we did that in, like freshman year or high school or whatever, where you did geometry, and then just measure it and get an approximate length. But that's not going to work that well, honestly, right? This is going to be a really flawed method for adding vectors. So we maybe don't want to do it this way unless it's a fairly simple thing. But this does illustrate something else that's interesting about vector addition, and that is the commutative property. In other words, you don't necessarily have to add vectors in the same order every time. You can mix up the order when you're adding vectors. Here they add C to A to B like this, so they essentially just put them in a different order on the page, and it gives you the same result, the same length at the same angle. So that's nice to know. And of course, just like, you know, regular subtraction, vector subtraction has to be in a particular order to mean something that you want it to mean. In other words, it is not commutative. However, what we do know from vector subtraction is that if you mix up the two things that you're subtracting, you just get the negative of the original vector. So if this is your answer to A minus C or something like this, then if you did C minus A, you would get this as your answer. It would just be the same vector in the opposite direction. So that is also interesting. But another thing that's interesting is we can actually define A minus B as A plus minus B, just like we can in normal arithmetic. A minus B is the same as A plus minus B. And since minus B is just the same vector as B, it's just pointing in the opposite direction, then we can show that that math is true, and we can also show it. Here we go. We can also show geometrically that it's true. If this is your A vector here and this is your B vector here, and you're subtracting the two, then you can just draw the negative B vector and add it instead. So you're still doing the head to tail method here. Now, the head to tail method I've already mentioned is not that useful. We've already seen that it's not that useful, especially in complex situations. But it's a good idea to just keep this idea in our heads so that we can have some kind of visualization. It's important to try to visualize vectors as much as we can. So this still does work. There is another method for adding vectors together, or sorry, subtracting vectors, not adding, but subtracting vectors. And I'll show you it here as soon as I can bring up my drawing tools on the screen. There we go. So if this is our vector A and our vector B is this vector here, which would look more like this, that's our vector B pointing that way instead of this way, right? If I want to take A and B and I want to subtract them like this, instead of taking A and adding negative B, I can actually put them tail to tail. So I take this B vector and I move it over here so that it's right there. There we go. I go tail to tail with the vectors when I want to subtract them. So here's A and here's B. And then I draw my resulting vector, the answer, in other words, is drawn from the head of the one that you subtracted to the head of the one that you subtracted from. So it goes from here to here. And you can see that this vector and this vector are the same length. They point in the same direction, right? You can actually figure out that they're in the same direction and the same angle and everything, doing a little geometry since this is a parallelogram, right? And you don't really have to, but it can be done. It's not hard to prove that this is true. But this vector here ends up giving us the same answer. Now, a lot of students say, but wait, this one's down here and this one's up here. Vectors don't care about where they are, really. The only vectors that care about their starting position are vectors that denote position, so position vectors. So if you're saying I am here, and there's a position vector going from the origin to the point where you actually are, then that vector cares about where it starts. But all other vectors don't. Displacement vectors don't care where they start. They just want to tell you the direction and the distance. So that's all they do, and that's what these are. So these vectors don't care if we slide them around. You just have to make sure that they're always at the same angle relative to the coordinate system and the same length relative to the coordinate system. So there are some homework problems for doing the adding of vectors and subtracting of vectors in this chapter. I don't know how many, a fair number, I suppose, just to kind of give you a visual idea of how these work. But then it won't be long before we're not really drawing them out to use the drawings as a means of solving anything anymore. It'll be just for visualization, just for keeping track of things. So just so you know. Here they show the difference between A plus B and A minus B, right? A minus B is downward to the right a little bit, just a little bit down, mostly to the right. A plus B is almost completely straight up. So it's definitely very different. Now, multiplying vectors is a not easy thing. We will do some multiplications of vectors, but we will not do it explicitly. We will not actually do the math of the multiplication of vectors because it's beyond this class. But it is doable. It's important that you realize that vectors can be multiplied together. It's not always obvious what the answers are going to be. There's a way of multiplying vectors so that you end up with a vector. There's also a way of multiplying vectors so you end up with a scalar, just a number. Those are two different kinds of multiplications for vectors. So it's a little complicated. But multiplying a vector and a scalar together is quite easy. Remember, a scalar is just a number. It just scales something. It gives scale to something. That's why it's called a scalar, right? And so if you had, for example, a vector like this that tells us some kind of a distance, B or A like this, A is 27.5 meters pointing off in this direction 66 degrees above the x-axis. What if we wanted to know what half of that distance was? What's half of that scalar? Well, you can multiply A times 0.5. It's totally fine. You can just take A, the vector, and when I'm doing vectors in my homework, I usually put a little arrow over them so I know that they're a vector since I don't have a boldface setting on my pen or pencil. But if I wanted to multiply A times 0.5, then I could. It's totally legal because this is just a number. It's just a scalar. It's going to scale this vector down. It's going to give me a vector that's half this long, pointing in the same direction. And essentially every vector, the vector A, for example, can be represented as two things. You can represent it as the length, 27.5 meters. And, put a little comma here at 66 degrees, the direction, right? So this would be the whole vector representation. We don't use this type of representation. We'll show you here in a little bit what we do use. But you could use this because this gives you all of the information that you need. In which case, this would be the magnitude of the vector. Usually we denote the magnitude by just saying this is A without any arrow over it, no boldface. And this is the direction. We just call this the magnitude A, magnitude of A, and this is the direction. This is also sometimes given absolute value signs as the magnitude, but not always. And if I wanted to do 0.5 times this, and then it would just be this times 0.5. So 0.5 times A would equal 27.5, which would be 13.75 or something like that. Meters. And the angle is not affected by the scalar. Oops, comma. The angle is not affected by scalar multiplication, so it stays at 66 degrees. All that the scalar multiplication does is it affects the magnitude of the vector. If I multiplied this by 2, then this would go up to like 55. If I multiplied it by -6, then this would actually switch the direction of this vector. That's the only situation in which you can change the direction of a vector using scalar multiplication, is to reverse the direction by multiplying by a negative. That's the case when we multiplied b by -1 to get -b, for example. So those are all situations that you can encounter with vectors. Okay. So now we're going to actually jump into how we do deal with the mathematics of vectors in a way that is useful. And it actually has very much to do with the fact that we are using a coordinate system that is orthogonal, and that the two dimensions of our coordinate system are independent of each other. We can separate them. They're separable, right? And that's exactly what we're going to do. We're going to separate them. So here's a vector A, just off at some angle with some magnitude, some length, whatever it is. We're going to do this all symbolically. And it actually has two vectors that we can make up, that we can create, that if we added those two vectors together would give us A. And one of those vectors we're going to point along the x-axis, and the other one we're going to point along the y-axis. And we're going to call them the x and y components of A. And why would we do that? Because it's convenient, right? Why not have something just pointing in the y direction and one and the other one in the x direction? Because we've already set up our coordinate system that way, right? And we already know from our problem with, going through the city, that vectors in the horizontal and vertical directions can add together to make this A. We're just doing this backwards. We're starting with this vector and creating the two that add together that equal this vector. Now we have two vectors independent of each other that when we add them together equal our vector of interest, the vector that we had to start with. But each one of these vectors only points in one of the dimensional directions. This one is an x pointing vector. So we call it a sub x, or the x component. This is a y pointing vector, so we call it a sub y, or the y component of A. Components, of course, just mean parts, so that makes sense. The parts of A. So these are the two perpendicularly independent parts of A in our coordinate system. And if we know that that a sub x is 3 meters in the east direction and a sub y is 4 meters in the north direction, then we can use the Pythagorean theorem to calculate what the magnitude of A is. 3 squared plus 4 squared equals 5 squared, then you get 5, right? Pretty simple one there. Using the Pythagorean theorem. We can also start to play around with trigonometry. Now, some of you have had more trigonometry than others. We're not going to use a lot of trigonometry in this class. We use trigonometry a lot, but we don't use a lot of trigonometry. Does that make sense? Remember, in trigonometry, when you took that class, you probably got really sick of doing proofs. The good news is physicists don't like doing proofs any more than anybody else. In fact, physicists really hate doing proofs more than most people, because physicists kind of think of math as a hammer. In fact, that's why we invented it. Physicists invented math. Almost all of math was invented by physicists to do work in physics, to do something, to accomplish something. So we think of it kind of like a hammer or a screwdriver. I don't care how it's made or who even made it. I just want to use the dumb thing, right? Which is not entirely true. We do care a little bit about the math since we did invent it, but mostly we just use it. So we're going to be using pretty much 3 functions and their inverses. We won't use many identities. Every once in a while we might use an identity, maybe like the cosine, the law of cosines or the law of sines every once in a while, but besides that, not much. For those of you who have had less trigonometry maybe than others, trigonometry is really quite simple. It's a simple extension of the law of it's a simple extension of the law of what's the word they use in geometry? Similar triangles, and yeah, it's a law of similar triangles in geometry essentially. In geometry, the way it goes is, let's see here, how do I draw a triangle? Think like this. In geometry, there's this rule that says if you have 2 triangles that are similar or something like this, this one here, 2 similar triangles are similar when they share the same angles, when they have the same angles in them, right? So if these 2 triangles have, if one of them has a 63 degree angle and then a 57-degree angle, and then a 60-degree angle, then this one being a similar one would have the same three angles, even though it has smaller sides. And the interesting thing about similar triangles is that you can create these ratios. You can say that this side here, if we call this side big side A, and this big side B, and this big side C here, and this one little a, little b, and little c, that you can create ratios like big A over little a, and then we start to sound like a Dr. Seuss book, big B over little b, right, equals big C over little c, right? That's entirely true. You can also create things like this, big A over big C equals little a over little c, which is actually just a rearranging of these things. So you get all these ratios that come out. What trigonometry is this same idea, except we only use right triangles. We use right triangles because right triangles all share one angle, which is 90 degrees. And then, you don't have to deal with as many different things going on. So in trigonometry, we get two similar right triangles, and you get these same ratios, but then we give these ratios names. We call them things. So one of the ratios we call the sine, for example. And with right triangles, since everybody has the right angle, the side that is opposite the right angle will always be the longest side, because the right angle is always the biggest angle, because there's only 180 degrees in a triangle, right? So that's half of the angle right there. So this side we call the hypotenuse. And why? Because it's a long name and it's the longest side. I actually have no idea what hypotenuse means, but that's how I've always remembered it's called the hypotenuse, because it's a long word, and that's the longest side. And then the side, then we're going to pick an angle that we're interested in. Let's say we're interested in this angle right here. We pick this and we call it alpha or something. Then we say that the sine of alpha is going to be equal to a ratio of these two sides. It's going to be equal to one of these ratios. And remember, all these ratios are the same for similar triangles. So it all, for a particular angle, if this angle is 20, then this angle over here has to be 70, because there's only 180 degrees in a triangle. So that this ratio will be true for any angle 20 degrees in a right triangle. It doesn't matter what size the triangle is, it's always going to be a similar triangle, so it's always going to be the same ratio. And so this particular one is the sine, and then this is one of the ratios. The sine of alpha is going to actually be equal to this one. The length of this side over here, which we call the opposite side, because it's opposite the side of theta or alpha, whatever we call that. And then the one that's next to it is adjacent, which is just a long word that means next to. So we have the opposite side over the adjacent side, and that's the sine, opposite over adjacent. No, sorry, that's not sine. I always do that. It's opposite over hypotenuse, isn't it? That's because I'm not very good at memorizing things. I always have to think it through first. I had to go through and think, wait, where is that particular number? Okay, so that's right. But then we have the cosine, which is, the cosine of this angle is the adjacent over the hypotenuse, right? Make sure you raise your hand. I saw you raise your hand because you thought I'd made a mistake and you were right. Make sure you raise your hand if I make a mistake, because I'll make plenty of them. It's easy to make mistakes when you're doing these things. Especially since I don't teach from notes ever. I used to teach from notes, but I found it really obnoxious. And I never made mistakes when I taught from notes, so my students never were able to see me make mistakes and see me fix them. So they never figured out how to fix their own mistakes. Then you have the tangent, which is the one that I was doing first, which is the opposite over the adjacent. Right? And then something that students learned after I was done with school. When I went to school, we didn't learn so many of these tricks and tips and like these acronyms or anything like that. They just kind of drilled things into our heads until we got it right. And it's just the way it was when I was going to school. But when I started teaching, I learned that everybody knows this thing called SOHCAHTOA, right? Let's see if I can remember how that goes. Like this. I actually have to look at these things to see how it's spelled. Kind of sounds like Sacagawea or something. It sounds like some kind of Native American, but it's not. It's just an acronym. It's a trigonometry acronym, right? So this is sine, opposite, hypotenuse. And that's probably why I always get it wrong, because I never think of this thing until too late. Cosine, adjacent. So it's sine opposite equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And these are the three trigonometric functions that we use, and they are really they're just ratios of numbers in right triangles. That's all they are, ratios of sides. It's not really anything more complicated than that. And you can spend a whole year in a trigonometry class listening to your teacher say that it's much more complicated than that. But in the end, it's not. It's just that. It's just that simple. That's what it is. So that's trigonometry in 10 minutes or less. All you need to know. And pretty much all anyone needs to know. Almost nobody uses more trigonometry than that in the entire universe. So I teach a trigonometry class over the summer for students who want to take physics in the fall but haven't taken trigonometry yet. And my trigonometry class includes almost no proofs or anything like that. It's just learn this stuff. Learn this stuff that you need to know. The math department's not very happy with me. Okay, so why do we use it? Because if we know this vector A, let's say that the magnitude of this vector is given to us, we know the length of it, then we can use trigonometry to calculate these two components, right? Remember that we said that the cosine was equal to the adjacent over the hypotenuse, right? The hypotenuse is the length of A, which is this number here, A. So if we divided both sides by this, we would get cosine equals A sub x, which is the adjacent side to the angle, over the hypotenuse. So we can rearrange that and actually solve for A sub x. We can calculate the length of A sub x. We already know the direction of A sub x. It's in the x direction, right? So we're good to go there. But we don't really know the magnitude of it. But the magnitude is equal to A times the cosine of whatever angle is right there. And we can do the same thing for the y component. We can create the y component, or we calculate the magnitude of the y component using the sine of the angle. So it becomes quite simple. And this will be pretty much the way it's done throughout the rest of this class. Your x component will be associated with the cosine, your y component is associated with the sine. But there are some situations where it's not necessarily that simple. Whenever you're dealing with a kind of a horizontal system like this, and your angle is between the x-axis, and your vector, then sure, go ahead and use this. But sometimes we're going to do strange things to our vectors. Sometimes not to our vectors. We're going to do strange things to our coordinate systems. Sometimes we're going to rotate our coordinate systems. It will just make sense. Rotate them into a particular angle. We'll do that pretty soon here in this chapter. And you'll see that it's maybe not as convenient to use this. You can still use these if you want to. You just have to be careful where you measure your angles from. You always have to be careful where your angles are measured from and what is actually adjacent to that angle, what is actually opposite to that angle. You also have to be careful which direction the vector is going, because sometimes, for example, you have a vector that's pointing off this direction. And somebody will come along and say, oh, good, I've got this angle here, and this component here, and this component here. And then they say, well, A sub x equals A cosine theta. Well, guess what? If you measure the angle from the negative x-axis, it will not give you a negative number for this component. But this component is obviously pointing in the negative direction. So you have to be careful of the sign of your vectors. You have to know which way they're pointing, in other words, or at least have some idea. If you want to get it right every time, then always measure from a positive x-axis. Measure this angle to your vector, and that will actually give you a value that is negative. But that's not always that easy, and it's not always that obvious to do. So I just like to, I know this vector is pointing to the left, so I know it's a negative vector in my coordinate system, so I'm just going to calculate whatever this is and then put a negative sign on it when I'm done because I know it's supposed to be negative. You just have to be very careful and very just aware of what's going on. Now, why do we want to do this? Why do we want to break this down into components? Because it seems like a lot of work. Well, one of the reasons is because we can do math with these. Remember when we were just doing geometry, we couldn't actually do the math. We could do the math with Pythagorean theorem. So two vectors like this, we could add together to get, A equals 10.3 blocks. You can do that because it's Pythagorean theorem. These two things are perpendicular to each other. This vector and this vector are perpendicular. When you add them, it's Pythagorean theorem, you're good. However, if you have two vectors that are not perpendicular to each other, like A and B here, you can't just say this one squared plus this one squared equals this one squared, because that's not true. Pythagorean theorem does not apply in this situation because there's no right angle in this triangle. So we can actually use our system of breaking things into components. You can break the A vector into its X and Y components. Then you can break the B vector into its X and Y components. And then the resulting vector is the sum of the X components, which creates a new X component for the result vector, and the sum of the Y components. You're just adding them like numbers. It's not even vector algebra or anything, vector arithmetic. If A sub Y is 5 and B sub Y is 6, then it's 5 plus 6 is 11. And you're good to go. That's RY is 11. Simple, right? And it's straightforward. So once you've broken down vectors into components, they just add together like numbers. You can get negatives. If this vector was pointing down this way, then this would be a negative vector. It would be pointing this way, in which case you would be AY plus a negative number thing here. But if it's a negative, you can still just add them here and it'll still give you the right answer, right? In the end, you get some components that are your result, your answer. So your result in X is equal to A sub X plus B sub X. Your result in Y is equal to A sub Y plus B sub Y. And your total resultant vector is the sum of the two resultant vector components, which they don't show here. And I'll write it down. So your total vector, this R right here, this R vector, which is a vector, is equal to A sub X vector, sorry, not A sub X, R sub X vector, plus R sub Y vector, where this is your R sub X vector pointing off in this direction, and this is your R sub Y vector pointing up in this direction, right here, right? That is simple arithmetic after you've broken things down into components. So the reason we're dealing with components is because it takes complex geometries, complex mathematical things with vectors, and it breaks them into two simple problems. One problem in the X direction. Here's your problem in the X direction, right there. One problem in the Y direction. And then you do this simple arithmetic in the X and Y direction to create your X and Y components of your answer. And you just build your new vector again. Now, if you want to know the total length of your R vector, your resulting vector, you can use the Pythagorean theorem now because your Rx and your Ry are perpendicular to each other. So you can use the Pythagorean theorem and calculate the length of R. And if you want to know the angle of that is equal to the inverse tangent of the Y component over the X component, which would be, if this is the angle, if theta goes from the x-axis, then that would be the opposite side over the adjacent side, which is another one of those components, one of those ratios that we talked about with trigonometry. So these two equations become quite useful in that way. So if we do this actual example with using numbers, using angles and lengths of vectors, we have let's see, the angle for B is 63 degrees. The angle for A is 20 degrees. A is 53 meters long. B is 34 meters long. Then we calculate the components. We essentially divide these vectors out into their components or break them down into their components, however you want to think about it. So the x component of A is the magnitude of A, which is the 53 meters, times the cosine of the angle to A, which is the cosine of 20 degrees. That's just numbers. You just crank them out. All right. Make sure that your calculator is on degree mode when you're using angles in degrees. Usually you have a button that says mode or something you push, and it gives you an option for degrees, radians, or mine has grad. I don't know what grad is. Gradient, maybe? I don't know, probably. But anyway, you want to put it on degrees and then hit enter or something like that. Where is enter? I don't know. Anyway, you want to push that and then do something. Enter. There we go. Quit. There we go. Yeah. Make sure it's in degrees when you're doing that. Your component, your x component of the b vector is b times cosine theta b. This is the theta, the Greek symbol, by the way. 34 meters times cosine 63 degrees, which just numbers, multiply them together. And you can do the same thing for the y components, except you're doing sine instead of cosine. Now we've got our x components and our y components, and since we're adding these two vectors together, we add the x components, which is 49.8 plus 15.4. Add the y components, 18.1 plus 30.3, and you get your x components for the result as those answers. Then the total length of the answer is Pythagorean theorem. Rx squared plus ry squared, square root, 81.2 meters. The angle is ry over rx, take the inverse tangent. That gives you an angle of 36.6 degrees. So this is what we often call the analytical method of vector addition, analytical vector math or whatever. But it's essentially, I like to call it the component version or the component method, right? We're just breaking things into components. Then we do the math with individual coordinates, do the math in the x, do the math in the y, do it all separately, and then bring it back together to build a new vector at the end. You're looking skeptical.
Just studying for a test for a while and knowing this will help a
Oh,
lot. Yeah.
so you're studying for the MCAT? Is that what you're doing? Or studying for? Oh, what's that? Oh, the dental one, right? Yes. Yeah, it's definitely helpful if you're studying for one of these kind of medical exams that you have to take. In fact, I think that it's been determined that the two sections that students struggle with the most are the math and the physics sections of that exam. I think the physics is the number one most struggled with section, and math is close behind it. And that's one of the reasons that doctors and dentists and physicians assistants and other people that have to take this class take it like in their last semester right before they have to take that test or something, so that's fresh in their mind and they're ready to go take that test. I totally get it. When you go into graduate school, there's a graduate exam you have to take in physics. Physics graduate students have to take a special graduate exam called a GRE, but it's just for physics, and they can ask you any question in the world. And they do. It's terrible. It's a one-day long exam. You're doing really good if you get like, if you're in the 50 percentile, you can go pretty much anywhere you want. Anyway, I mean, you can, even in the 10th percentile, you're going to have options, but almost nobody gets a perfect score on it. It's just so hard. It's so much pain. One of the worst days of my life. All right. So here are those same two vectors, but now we've subtracted them. You have a minus b, and this is what it looks like graphically. But if you're going to subtract them, if you were going to subtract them up here, then it would look like at this point right here, you would just put a minus sign here and a minus sign here, and you get 49.8 minus 15.4 and 18.1 minus 30.3. So in other words, the y component would end up being a negative number, which would make sense if you look at this picture, because when we added them, two positives make a positive. When we subtract them, the y component becomes negative. The x component didn't. The x component is still in, it's still in the positive x realm over here, but it's in the negative y realm down here. So, and it looks like a minus b equals r here. A minus b equals r here. So this one's negative, this one's positive. This is another one, another thing where you can do a bunch of vector addition graphically. This can be helpful if you're struggling to figure these things out. It's not a terrible thing to go and do some vector addition. This can also actually help you do your homework. This particular thing, if this is very precise, so you can put in some vectors here and add them together, for example. So I put an A here. Oops. I guess I have to drag it in here. And if you can change it to be whatever you want it to be, and then put in B, and it'll actually give you the answer, so you know what your answer is. It can help you with your homework. It's kind of a little graphing calculator. Think of it as vector calculator. Useful tool. All right. So that takes us to projectile motion. At this point, let's take a little bit of a break till about a quarter till. We'll come back and cover the last two sections, and then we will be done for today. Ugh. Ugh. Okay. So, before we go on to this next section, I do want to talk a little bit about, let's talk a little bit about labs. Does anybody want to do the lab here in class, particularly? No? Doesn't matter. You would like to do it here in class? Okay. What, well, you and I can work on what day you want to do it. If you're the only one that wants to do it here in class, um, then we'll just pick a time that works for you. If anybody would like to join him, then we can work together, and you guys can work together on that. Just so you know, the labs are done. The way that I set up the labs, they're pretty much done independently. I am available for help if you need help, and I'm more than happy to help. But I do want you to kind of explore things and figure things out, because that's, to me, the most important thing, is to play around with things, try to figure things out. It's less important to get everything right, to get the right answer all the time. It's more important to interpret what you did get and try to understand how it correlates with what you've been learning, doing homework in class. So I'm not looking for particular right answers or particular things in the lab. Mostly I'm looking for you to explore physics a bit and try to understand things through doing hands-on activities. Like I mentioned before, we'll be using this IOLab sensor car thing, but it also comes with some labs that have been pre-designed for it, and I'm also designing my own labs for it. So we'll use some that I've been doing. But to get to these labs, the ones we're going to use, you jump to your internet and do a search for IOLab. And you can go to, let's see, yeah, you can just go to the first thing, which is the macmillanlearning.com. That'll take us to a good enough place, I think. And there are a couple of different resources here that you can use. First of all, if you click on the, let's see. If you click on videos of IOLab, I believe. Yeah. Click on videos of IOLab here. It takes you to this embedded YouTube video, and you can actually just click on watch on YouTube and then go to his channel. If we go to let's see, that's not exactly. I know there's a better way to find this.
A hunger for a change.
I'm going to actually go back to YouTube, go back to actually Google here. Because, yeah, that's actually where I want to go, I think. Maybe I will just send it to you. I think I sent it out before, maybe. Let's take a look, in my open math. Sorry, I'm trying to remember where this all is, and I can't seem to. Here we go. It's a Google Drive. So there's a Google Drive thing here, and I'm just going to send you this link really quick. That will actually take us to where we want to be. Contents. Oh, no, it's right there. Okay. So I'm just going to send you this link so you don't have to go finding it. And let's just add it in here somewhere. Add a block. Okay, so now it should be in there. Should be able to click on ILab files, and it should take you right to this Google Drive folder. And as you open it up, these things, they'll include some different files. Usually the one that you want is the actual experiment file. It's usually a PDF. They also include a PowerPoint slideshow that you can review if you're interested. Maybe we'll review it in class sometimes. Who knows? This first one is about uncertainty and how it's measured, how it's calculated, and we covered that a little bit. Here they go a little bit more detail. For example, they talk about the standard error, and they talk about standard deviation, things like this. This is not a lab we're going to go through, but this just shows you some of the files that are available. What we will do, though, is we will do lab 1, which is an introduction. Here they've got a bunch of different stuff here. You don't need to worry about what you want to do is go to the activity. It's not the experimental file, it's the activity file. So you can either open the document or the PDF. The advantage of opening it as a document is when they ask questions in here, you can actually just type them in and then just turn this thing in if you'd like. Unless I specifically tell you to do something else, that's good enough for me. So for example, well, here they're actually showing you a way to write a report. So they want you to write a report using a very standard method, but I'm not that picky about it. So, but you could go ahead and use this right here as just an outline to fill this stuff in if you want. It's not terribly important, the whole report idea, but they do give you an example of how to do some certain things in here. This particular lab is just taking some data with the IOLab system and learning how to use the IOLab system. It's not doing any particular science of any kind. So so it's pretty straightforward. There's also a video that's associated. There's some videos associated with this, and I'll put a link for those in here as well. See if I can find them really quick on my end. I think the best way to do it is actually just go to YouTube and search from there, honestly. So you just go to the IOLab channel, and the very first video that they bring up is this preparing your IOLab, and I highly recommend you just go through these in order. So go to these created playlists, I guess is a good place. Go to Guide to Getting Started. It's a good way to
Connecticut State employees, a new dental plan is available to you.
Okay,
The
Stan.
Total Care DHMO plan has a little.
Everybody has to make money with their advertisements. But he just goes through everything from opening the box to the parts that are in the box to plugging into your computer. I think he even talks about changing batteries or something. And then you go to the next video. When you go to the next video in the playlist and you get through. So then he sets up the software next. He shows you where you can download the software, which I'll put a link to that in here as well. So that comes from this website, actually. Maybe. Videos, images. There's the software. Google Driver. Nope, that's not it. Why can I not find it? They've changed this, obviously, but I would think that they would keep all of these. Resources right here. Apparently they don't. Press further information. No, that's not going to be helpful. They used to have a link right on here that said download the IOLab software. Don't see it anymore though. But I'll figure out where the software is, and she'll show you in the video probably where it is. Hopefully his video is up to date. But I'll go and find it as well. But then you go to the next video, and for this first week, that's really what I want you to do. Is I want you to go through each one of these things and follow along with what they're doing. And in the course of doing that, you will pretty much do everything that they do in that lab. And then you can just, answer questions, or you can go in and just say, this is what I did and this is what I accomplished, and just turn something in so that I know that you did it. for this first week, for this first lab, or this first week of using the IO lab, since we're not actually doing any real science, we're just getting used to using this thing. I'm essentially going to be just grading you for completion. Did you get it out? Did you figure out how to use it? Did you do it? Full credit kind of thing. And so you go through these 7 videos. Each one of them is just a couple minutes long, and you're done. After you're done, you know, just write a little bit about what you did and what you learned about the IO lab. I also would like you to be in every time you use, every time you do any kind of experiment, I would like you to play around a little bit. I'd like you to explore on your own. Do something extra, do something different. Try to discover something on your own. Because, you know, just repeating something that somebody's told you to do is not really all that great of science. It's important to repeat things that people have done before, but the real purpose is to explore on your own and figure out things by yourself for your own good, for your own understanding. So the more you, in fact, if you're halfway through a lab and you're discovering something really interesting that you're really interested in, and you want to just go off on that tangent, that's fine. I don't care. If you tell me what you did and tell me what you learned, I'm totally happy with that. So so that's kind of where we'll go. Pretty much your grade on all of your labs will be based on your level of engagement in that lab, and that's, to me, determined by whatever you end up turning in, demonstrating that you actually learned something, you did something, you explored something, you connected it to what we were doing in the homework. It's not necessarily based on numbers or graphs or anything else in particular, but just a demonstration that you actually explored these ideas on your own. And mostly, I think the best way to demonstrate that is to just write a short paragraph and say, well, this is what I did and this is what happened. And I think that was, you know, related to this part of what we were doing in this homework problem, or what we talked about in class, or it was related to something that I'm interested in, and I found that interesting, so I explored it further and I discovered this, and so on and so forth. You know, it's more of a personal thing than it is trying to match up with what I'm trying to get you to do. And for the most part, my students will get full credit for their labs if they're doing their labs and exploring things. So I'm, and I know that's a bit different than most science lab classes, but I think my students have liked it better, and I think it's been better for them. So when I have students that are going into engineering or physics, we do a little bit differently. We still have that same kind of idea, but they have to be a little more strenuous because they have to learn some more specific techniques in experimental design and experimental reporting, but it's still the same idea in my opinion. So it's also the way that I learned science, and I think it did very good for me. So very good things for me. So anyway, let's see. Let's go back to the main channel.
Connecticut State employees, if a new dental plan is available to you, for total care.
Don't care about the new dental. Let's make a link to this and put it in our class here. Okay, so you got your files, you got your videos. I'll figure out the software here. Now maybe I can. Maybe I can get to it this way. Yes, maybe. Maybe not.
Maybe not.
In the YouTube video, it's possible. It's possible. Actually,
open up the bar.
I've been in this business for, writing's not that easy, but Grammarly can help. This sentence.
Apparently, if you're in Windows 10, you don't actually have to use a driver. Mac software.
Okay, I'm going to show you how to get the application on your Mac. And you can get the Mac software. So
Let's see, iolab.science. Let's try this. There it is. Okay, so this is where you can get it from. Apparently, driver, Windows, application, Windows, and Mac. There you go. Found it. Might as well get this all done now so we don't forget. And one last thing, which would be the iolab driver. Now, apparently you don't need the driver if you're running Windows 10. Otherwise, you might. It's up here. Don't need it for Mac either, I don't believe. But here are the instructions for that. Copy. All right. So that's all available for you now. And like I said, for this week, you'll open up lab 1 and you'll go through the first 7 videos essentially and do lab 1 along with those videos. It's pretty much the videos will actually cover a little bit more than the lab, but I don't think the lab covers anything more than videos. So I think if you do the videos, you're pretty much done. You go through them, write me kind of a paragraph or 2 on what you did, and maybe you want to paste some of the graphs that you make in it or something just to show me what you did and show me what you learned. And then mess around a little bit. Try and do something interesting. Try to measure something other than movement maybe, or something, just kind of play around with it a bit. And then the week after that, next week actually, we will actually do some experiments with it and move on from there. For those of you here in class, you can take one of these with you today. So don't forget to do that at the end of class. In fact, I will just hand them out to you right now. I think this box has every box has a few parts in it. There's like a spring, there's a hook, there's a little plate. There might be some stickers with felt. There should be some stickers with felt. If there aren't stickers with felt, then if there aren't stickers with felt on them, then they're maybe already stuck on the car, like this one already has them stuck on. That's for doing experiments with friction. And so take that one, we'll check these letters and make sure they got everything. try to be careful with them. They're a little bit pricey. I prefer not to have my students charge for things, so I just buy them and try to maintain them myself. But I try not to break them, try not to let them roll off into the table, for example. And if you need batteries for them, you can use AA batteries. And then remember, for those of you not in class, please send me an address so that oh, and if you're going to do this in class, you can leave it here. You don't have to take it home with you, of course. So you can just leave it here. But you can also take it home and try it at home and see how you like that. It's up to you whether or not. And then we'll figure out the time. But please send me your addresses if you're not in class so that I know where to send that to, and we can be done with that. Yes. So you can, the labs will be due pretty much the week after, you know, the lab that we're giving you this week, just turn it in next Monday or whatever, or turn in with the homework on Friday. Whenever, it doesn't really matter to me as long as you get it turned in the next week-ish. I know that summer schedules are usually a little bit hectic, so you know, whatever works for you, if you're going to do it over the weekend or if you're going to do it on a Tuesday night at midnight or whatever, it doesn't matter. Just get it in. I'm not that big into due dates, honestly. You have plenty of classes where you'll be stuck on due dates, so I don't want this one to be extra stressful. So I have done that in the past, and I'm considering doing it again where you can just upload it. I actually do have some places to upload them. I'm just not using them at the moment. Would you prefer to have them uploaded, or would you prefer to just email them, or just do you have any preference at all? Okay. Well, I'll try to take some time to activate all those again, and then you can just upload them and be done. It's pretty easy to do that. I mean, even if you write things out by hand, you can just take a picture and just upload pictures, whatever. So we can do it that way. Any other questions about the lab work and the IO lab and everything else? Okay. Let's see, what else do I want to talk about before we're done with this? I guess that's about it. All right. So let's move on to the last two sections of the chapter. Oh, I got too many classes I'm teaching. There we go. So projectile motion. Projectile motion is, as I mentioned before, this motion where we launch something, and then the only thing acting on it is gravity as it flies through the air, right? Think of the human cannonball, or a soccer ball, or a real cannonball, or all kinds of things like that are considered trajectory motion or projectile motion, right? Remember the kinematic equations. We have these 5 equations, and these ones are written in the x dimension, so they're all x's, and we're going to consider that the horizontal direction, right? So the horizontal direction will be the x direction. And remember the kinematic equations that we have in the vertical direction were the same equations, essentially, just replacing the x's with y's and replacing the accelerations with negative g, right? So now we have all these equations. We have the horizontal and the vertical, but in the horizontal direction, remember we mentioned that we're going to not deal with acceleration in the horizontal direction. We're going to let it go. And the only thing that will be accelerating this thing will be gravity. We could include some acceleration if we had like air drag or something, but we're not going to do that yet. So if we don't include acceleration, then this equation right here just becomes velocity final equals velocity initial. In other words, the velocity in the x direction doesn't change, right? Because it's not accelerating in the x direction. This equation down here just becomes this equation up here because this last term falls out, right? And this equation here becomes velocity final equals velocity initial again. So we end up with only two equations, or you could say maybe three, but just really just two equations in the x direction when we're dealing with projectile motion that has no acceleration in the x direction. So these are the equations we end up with. The two equations in the x direction, this one and the average, well, even this one goes away because you don't have changing velocity. You end up with just one equation in the x direction. And then you end up with the equations in the y direction, which are the four equations of kinematic motion, right? Well, you actually end up with five if you want to do the average velocity in the y direction. But anyway, you end up with five equations, one for the x direction right here, and four for the y direction, where the acceleration is negative 9.8 meters per second squared. So you go about these problems in a very similar way to other kinematic problems that we did in the last chapter, except that you have to start by breaking these things down into vertical and horizontal components. So you start off with these vectors. You start off with an initial velocity vector that's maybe upward and to the right. If you have this soccer ball that you're kicking, for example, its initial velocity starts off this direction. So that's its initial velocity vector. And part of its velocity is an x component here. Part of its velocity is a y component here. So you're breaking it down into components to start off. You have a velocity vector here. You have velocity in the x direction here. You have velocity in the y direction here. And these are all initials. So this is a v naught. This is vy naught. This is vx naught, or v naught x, however you want to write it, doesn't matter. And that is breaking it down into components. If we end up over here with this final velocity right here at this final height, then this also has components. This has a y component, it has an x component. This is the velocity final, which we just call v. So this is v final in the y direction. This is, that almost looks like a y. And this is v final in the x direction, right? We can use the trigonometry here, because this here has an angle which we'll call theta naught maybe to begin with. So Vx naught is going to be V times cosine theta naught. And Vy naught is going to be V sine theta naught. Right? And this one here is going to have angles as well. You might be tempted to use this angle here, but if you do want to use this angle here, you got to be aware that this angle is not with the x-axis. So our x component is now opposite that angle. So this is going to be Vx equals sine this angle. So maybe we want to use this angle here instead. This is our theta final, we'll just call it theta. This would be V times cosine theta, because that's next to it. And notice that this is definitely pointing in the positive direction, because this thing is moving to the right still. But this one up here is definitely pointing in the downward direction. So this one's going to be V sine theta, but you might want to put a little thing here that says this is going to be negative. You might want to just put a negative on it. You might want to put it in parentheses or something so you remember it's going to be negative because it's coming down at that point. But then you've built these things up you've broken these things down into their components. And then I actually just like to do my X and Y things differently on the page. I make a little section for doing my X math. Maybe next to it, I'll do a section for my Y math, or below it or something like that. And I just do them separately. And I'll write my things in that I know. I know that the Vx naught, I'll write this up here on this first line. And I'll write this one right here next to it on the second line. I'll do the same thing with the y's over here. And then I'll start using the kinematic equations to solve something for something. If I know my initial velocity and I know the final height, for example, which would be equal to y, it's the y direction height, right? Then I can use an equation to maybe figure out what the final velocity is if I know the initial velocity and the final height. Or I could figure out the time that it took to get there. Or I could figure out how far it went in the x direction. Remember, we only have one equation in the x direction. That's x final equals x initial plus velocity times time. That's the only equation really I have. So if I say that my initial position is 0, then I just need to know my initial velocity. This is x velocity, by the way, my x velocity and the time. Well, if I know the time, or if I can calculate the time, then I can figure this out. And then you just go through and solving these things separately. The thing that connects these two things, the thing that connects x and y is the variable that's in both x and y. What is the variable that's in both x and y? It's the one that's not dependent on space. It's time, right? So if you figure out how long the ball flies in the y, it's the same time that it flies in the x, right? Because time doesn't care which direction you're going. So the time, if you can figure out the time using the y, and then you can use that time over here in the x to calculate maybe the final position, for example, in the x direction. So that's the idea here, is to use, you're solving simultaneously in the x and the y dimension using the x and y components of your vectors. And then everything else is done the same. When you're done, you build your final vector, your final answer from your components of your two dimensions, in your two dimensions. So let's actually do an example of this so you can actually see it in action. We're doing a firework. Yeah, fireworks are cool. It's the right time of year for it too. So this firework is going to be launched at the 75-degree angle with this initial velocity v0, and it's going to get up to some height here. They told us the answers because they've already done it. But that's the picture that we're looking at. That's the thing that we're trying to do. They tell us the initial velocity is 70 meters per second. The initial angle is 75 degrees. And that's all they tell us, really. They say, well, they do tell us one other thing. They say at its highest point, it explodes. So we're trying to measure things at the highest point. Well, if we imagine that they didn't tell us these numbers here, so we don't know what the answers are, for example, right? And this is all we know, then we do know something about here. At the top here, we know something about the final velocity in the y direction. What's the final up and down velocity at the highest point? Is it still going up? Is it going down yet? So what is it doing if it's not going up or down? The final velocity at the top of its motion is 0 in the y direction. It's still moving forward, but it's just not moving up or down because it's turning around, right? So the final velocity in the y direction is 0. We know the initial velocity is given by this vector here. The initial velocity is 70 meters per second at an angle of 75 degrees. So we need to calculate the components of this vector. We need the x component and we need the y component, right? And we can calculate those. Vy is going to equal velocity times the sine of 70 degrees. Vx is going to equal the velocity times the cosine 70 degrees. That's times. It's cosine of 70 degrees, right? And then we can do our x component math here and our y component math here, right? We can actually figure out something in the y component right away. Well, not right away, but we can do something in the y component fairly quickly because we know some things. I like to write down what I know right away on each of these. And I know that the velocity in the x direction initially is velocity x y naught and velocity x naught. So the initial velocity in the x direction is equal to 70 meters per second, because that's my velocity, times the cosine of 70. That's 75, cosine 75, sorry. I'm getting my numbers mixed up. not cosine 70, cosine 75. Angle is 75, the velocity is 70. Okay, so that's my initial velocity in the x direction. My initial velocity in the y direction, Vy naught, is equal to 70 meters per second times sine of 75, right? I know that my final velocity in the y direction is equal to 0. I know that my final velocity in the x direction is the same here because it doesn't change, right? So I know my initial velocity, I know my final velocity in the y direction. Can I figure out anything else from that? Well, I also know that my gravity, my acceleration is gravity, negative 9.8 meters per second squared. And there's an equation that does tell us something about time if we know initial velocity, final velocity, acceleration, right? Which one is that? Well, that's this one here that says the final position in the y direction equals the initial position in the y direction plus initial velocity in the y direction times time plus 1/2 times the acceleration times time. That's one of our equations, right? We know that the initial velocity, we know the initial velocity, this is this number here. We know the acceleration. We don't know the final position. We know the initial position is 0. So this is 0. So that's not helpful to us, but it may be helpful to us eventually. But there's another equation that says the final velocity equals in y equals the initial velocity in y. Plus the acceleration times time. That one's even more useful because we know the acceleration, we know the initial velocity and the final velocity, so we can get time out of this one. From this one, we get time, right? Once we know time, we can plug it into this one, and then we can get the height, the final height in the y direction. So we know how high it'll go. Once we know time, we can plug it into this equation over here. Final position equals initial position plus velocity in the x direction times time. Once we know time, we can plug it over here and find out final position in the x, how far it goes down range, in other words, in the horizontal direction. And then we're done. We've just solved the problem. We haven't plugged any numbers in yet, but we've solved the problem, right? All we need to do now is plug these numbers into this equation. We plug all these numbers into here. Then we plug time into here, and then we plug time into here, and we're done. Right? And that's how it's done. It's not always simple because you have to really kind of figure out the order of things, figure out what you know, what you can figure out, what you can calculate. But I think the best way to do it is what I've just done here, which is first, before you do anything, before you try to solve anything, just break down your vectors into components and separate the problem into two problems. So that you know what you know, figure out what you know in the x dimension, figure out what you know in the y dimension. And then start writing down equations that can give you something that you don't know from what you know. And see if you can get what you want to know from it, right? And if it means that you have to calculate something in the y first to get something in the x, then you have to do that. But that can happen a lot, especially with time, right? Time is very often that way. Another thing that goes back and forth between there is the angle. So sometimes they won't tell you the angle and you have to calculate the angle. So you can calculate the angle on one side and then jump it over to the other side. And then you can calculate the stuff on the other side using the same angle. Because the angle is shared as well. And that's basically how these things are done. Is you separate the problem by breaking it into vectors into components. And then you use the kinematic equations in x and y separately to solve for things, and then sometimes jumping time and angle back and forth to solve for other things on the other side. And then at the end, you'll build a new vector. At the end, you'll have maybe a final velocity vector. There's a problem that we'll do here another example we'll do where we actually build a vector thing. In this case, they just want to know the height and the distance it goes, but that's all you could consider that a displacement vector. They tell us the height is 233 meters and the distance is 125 meters. Well, that just means that our displacement vector, if we wanted to call our displacement vector D or something like this, the displacement vector which goes from here out to the point that it blows up, D would equal 125 meters in the x direction, right? We'll call that x direction, plus 233, man, that's terrible, meters in the y direction. That's just the addition of two different vectors, where this is one vector and this is another vector, right? This is my d sub x vector. It's my d sub y vector. Any questions about that particular example? Okay. The next example is we're going to calculate how fast a rock is going after it's been spat out of a volcano. There's a lot of volcanoes exploding in the world right now. It's kind of exciting. But this is Kilauea in Hawaii, the most continuously active volcano. It doesn't actually shoot rocks very far most of the time because it's so active, it doesn't really build up that kind of pressure. But anyway, it's shooting out this piece of stuff and it's flying over here and it's going to land further down, down the side of the mountain somewhere. It comes out at a velocity of 25 meters per second and it's at an angle of 35 degrees with the horizontal. It's going to hit at some other velocity down here and some other angle with the x. But we do know is that where it landed was 20 meters below where it launched. So that's useful. So the first thing I'm going to do is I'm going to write down the things I know. That's the most important thing to do. And so I know that V naught, I know my initial velocity vector is 25 meters per second. They've written that down in the picture, but I'm going to write it down over here. And then I'm going to split this into x's and y's immediately. I'm going to start breaking down my vectors. That means V0x equals 25 times cosine of 35, right? And V initially in the y direction is 25 sine 35. Great. I'm going to define my 0 point. My origin is going to be right here because it drops to negative 20 below there. My origin in the x direction is going to be right here as well. So I know my initial x position, x0 is 0. And I'm going to say that y0 also equals 0. Important to know. And then I know my final velocity, right? I know my final velocity is equal to some velocity and some direction. It's some direction theta. That's all I know about it, right? But I can still break it down into components. I can say that velocity, I can say that velocity final in the x direction, which I'll just call v sub x, is going to equal, we'll call this theta, well, this one is theta, yeah, so good. So this one is going to be v final times cosine theta, and it's going in the positive x direction, so I'm just going to deliberately put a positive there so we remember that it is definitely positive. And v final in the y direction is definitely going down, so it's definitely negative. And we're going to call that negative v sine theta. I also know my final position in y because it says it's negative 20 meters. Right? And that's pretty much all I know. That's everything we know right there. Well, that's good. It's enough. take everything that we know, and then we start using kinematic equations. This kinematic equation right here, we know the final y, that's one thing we know. We know the initial y, it's right there. We know the initial v, it's right there, it's just remember. We know g, the only thing in this equation we don't know is t. So we plug all those numbers in and we get this equation, which happens to be quadratic in t. It's a quadratic equation in t. We rearrange it so that we get this version of it where you have t squared, something times t squared, plus something times t, plus something that's just a constant equals 0. And then we know that this is a, this is b, including the negative sign, and this is c, and we can use the quadratic formula, which looks like this. Then we plug in those numbers and we find out 2 times. T equals 3.96 and t equals negative 1.3. And of course, we choose the positive time because time only moves forward for some reason. And believe it or not, we have no idea why time only moves forward, except philosophically, I suppose. But anyway, you have 2 solutions. We pick the positive solution, 3.96 seconds. When time, if time is 3.96 seconds, guess what? We can use that all over in our other equations. So we want to know how far it's going to go. Well, we know the initial velocity is this, and we know this equation for velocity. Well, let's see. Oh, we know the initial velocity in x. We want to know the final total velocity, so we need to calculate the velocity in y. Well, this kinematic equation will tell us the final velocity in y if we know the initial velocity in y, the acceleration of the time, which we now know because we figured out the time. Well, then you plug it in there and you find the final velocity of y. Once we found the final velocity of y, we have 2 vectors. We have the final velocity in x, which is equal to the initial velocity in x, 20.5 meters per second. So that's our final velocity in x, 20.5. And we calculate the final velocity in y, and we know that it's supposed to be negative, and we know that its value is 24.5. Well, of course, we can use this to calculate the overall velocity final. This is the final velocity x, this is the final velocity y. And the total final velocity is the square root of these 2 things squared, added together, because that's Pythagorean theorem. Vx squared plus vy squared. Right? And that's what they do. The very next thing they do right here. They calculate that. And they get a total overall velocity of 31.9 meters per second. And then we also know that we want to know this angle right here. We want to know this angle. And that means we take the opposite side over the adjacent side and take the inverse tangent of it. Opposite over adjacent, inverse tangent. And that calculates the angle of negative 50.1 degrees. They actually just throw the negative on there. Or no, they don't. They actually put it in as negative 24.5 for this number, and that will give you a negative in your calculator. So we've actually built a final vector answer for the velocity. We now know the final components of x and y of the final velocity vector using kinematic equations in x and y. Anybody here play golf? Yeah, you can go. Then you probably know this. See if I can. In my computer programming class, my students actually program this. They actually make this application. They program this on their computers. Well, here we have a cannon. We can change the angle. They used to allow you to move the statue of David over here so you could hit it, but they don't let you do that anymore. But you have a target that you can move. We can choose to have air resistance or not. We'll start off with no air resistance, and we can choose where we're going to shoot. A cannonball, a tank shell, a golf ball, a baseball, a pumpkin, a human, a piano. Let's throw a piano. We can change the initial speed. And we're going from 0 meters height to 0 meters height because we can't change the height of our target. They should change that so we can change the height of it. Well, maybe they can't, we can change the height of the initial, maybe. Maybe not. Why does it say height here? Because it is 0. They should allow us to change that, but they don't. But anyway, we're going to start off at 0 height. We're going to end up at 0 height, and we're going to fire this thing and see what happens. So let's see, how do I fire it? Where's the fire button? I can't see it anywhere. Is it this button? Must be this button. There we go. Hey, look at that. Boom. I won because I hit the target. That was pretty good for the first try. I did 75 degrees and I hit the target at initial speed of 18 meters per second, right? It turns out that if I lower this thing, what do you think is going to happen? What if I shoot it at 65 degrees instead of 75 degrees? What's going to happen? You think it's going to go further? Okay. True. All right. Lower to 55. Goes further still. Lower to 45. Maybe. Apparently I can't do 45. Goes further still. What if I lower it to 35? It actually didn't go as far as the 45. And if I lower it to 25? Notice that I've hit 2 spots twice. Can't go any smaller than that. Can't go, but if I went to 15, if I could go to 15, I would actually hit this spot again. Believe it or not. There are these angles, there are 2 angles where you can hit the same spot for every shot that you make in piano golf. This is piano cannon golf, right? But it's true for golf as well, right? And golfers know this. Golfers know that you can hit a ball very high and hit a spot, or you can hit it very shallow and hit a spot. But it has 2 different effects after the ball hits, because golf balls bounce, right? Pianos don't bounce so much. So if you want the ball to continue going in the same direction, then you hit it with the shallow. You hit it with the flat-faced golf club, usually called, your driver type things. You have your fairway woods, and you have your irons that are flatter face irons, your 5-iron, for example. And those numbers are all related to the angles on the face of the club. But if you don't want the ball to roll very far, then you hit it with a very flat golf club, something that's closer to the horizontal, right? A very steep angle to the vertical. And those are your pitching wedges kind of things, right? So if you don't want it to, if you want it to just bounce up and down, which is usually what you want to do when you're getting close to the green, then that's when you start using your steeper angled clubs, right? So it does that. And that angle, you really don't want to change your swing very much in golf, do you? Because the swing is the hardest thing to get right. And if you have to change it all the time, you're going to be screwed, right? You really like to just be able to swing the same every time and just change your golf clubs. So that's why you have a caddy, right? Because they actually know that stuff. It's actually that is actually the purpose of the caddy. The caddy is actually the one who knows all of these different things and also keeps track of things like wind and other things like that, right? They actually do calculations in the background. They're actually doing all this math in the background, and they're very good at it. It's exactly what caddies do, so that the golfer doesn't have to think about that. All the golfer has to think about is just swing the same way every time, right? Because it's hard enough to get that right. Not that golfers can't make those calculations. They just don't want to have to. They want to be able to relax and get ready for that next swing. Right? So, too bad basketball players don't have caddies, right? You come up to the 3-point line, you're like, oh, hey, what angle should I use? Just take a little time, wait for your caddy to come up with the right answer, line it up, breathe. Not going to work out so well, but it is actually a very similar thing. No, there's a reason. There is a reason that Steph Curry is the best shooter who has ever lived in basketball, and it's actually not what people think it is. There's a lot of things that make him the best shooter in basketball, but one of the most important things that not many people talk about is that he has an extremely high arc to his ball when he shoots. The reason for that is because he's so stinking short. That's why he started shooting that way, right? He's listed at like 6'3" or something, but he's probably 5'11". The guy is not that tall. He is so short. And his whole life, he had to shoot over people taller than him. So he learned how to shoot a high arc basketball. But guess what? When you shoot a high arc ball in basketball or in golf, when it's coming down on a very big looking target. If you're coming in at an angle, the target looks like a skinny little like cigar shaped thing. So if you're coming in flat at the target, you're very likely to miss. If you're off by a little bit, you're going to hit the rim and boom out. It's just going to clang out, or you're going to hit the front of the rim and never even get in there. But when you're coming down on it, the basketball hoop is twice as big as the basketball, twice the diameter. The basketball hoop is 18 inches. The basketball is 9 inches. So that's simple, right? You can fit 2 through there. And so he has this high arcing ball, and he's also very accurate. He works on his shot a lot, but he has this high arcing ball that is just looking at this huge real estate to hit because of the angle of the ball. It's physics, really, when it comes down to it. I'm not even sure that he knows it. He probably does. He's a smart guy, but nobody talks about that. Everybody just talks about he's just amazing for this, that, and the other reason, whatever else. And I'm like, but it's actually because of the angle of his shot. His shots have more real estate to hit. Even other short players in the league do not shoot at that high arcing angle that he has. And tall players never do. Tall players always shoot at this really shallow angle because they figure they can almost see into the hoop when they're shooting. So why not just shoot it straight in? Well, that's stupid. It doesn't give you the best option for your shot. And that's why big men are usually not very good three-point shooters. You know, they usually don't have a very good arc to their shot. The ones that are better three-point shooters do have a good arc to their shot. But you look on the same team as Steph Curry, and Draymond Green is a terrible three-point shooter. And his shot is just like throwing it at the hoop straight. It's terrible. It just has no real estate to hit. So, and this happens in many things in life. This is actually the reason that ballistic missiles are used in warfare. We don't shoot at things straight on. When airplanes shoot missiles at other airplanes, they don't shoot them straight on. Well, the United States does. Many other countries do. But in the United States, we figured out a long time ago, if you just shoot the missiles 100 miles before you ever see the other planes and shoot them up into the air and then let them tip over and come down on top of the plane, it's a way bigger target. It's way easier to hit from above than it is to hit straight on. Hitting straight on, they just have this tiny little profile to try and hit. So this is the reason America's Air Force hasn't been defeated in 50 years. Since the end of Vietnam, we have never lost a single battle in any conflict ever. It's never even been close. Because our planes come in, they fire missiles at 100 miles away, they turn around and go home. They don't even see the other planes. And these missiles are going up into space, and they come down and they say, oh, look at all these huge fat targets. And things just start falling out of the sky. And it's just physics. It has to do with science more than anything else. And it's kind of interesting because history shows that this one equation, or this, not just this one equation, but many simple scientific things like this have led to the rise and fall of all kinds of civilizations through war. You know, you can go back through every war that we've got a record of, and almost every single war in all of time, the turning point has been something technological. Even though we don't realize it, even though we don't think about it, but it almost always has been. You know, why did the South lose to the North in the Civil War? Well, they lost because they didn't have trains. They couldn't supply their troops. The South didn't have trains. The North did. Simple as that. You know, why did the United States win World War II? Well, things like this. Airplanes. We run the airplane race. We won the air battle. We also figured out radar better than they did. The English were very good at that. But in the end, it was a big bomb. We figured out the nuclear bomb before they did. Otherwise, the war might have gone on for a lot longer with Japan, even though Germany was out of it. Germany was out of it because they'd stretched their supply lines too long. They couldn't keep it. They couldn't keep the war going long enough because they didn't have the technology and the resources to do it. It came down to transportation, you know, which is essentially a technology. It's so many things come down to science in the end that it's kind of ridiculous. Even in the arts and the fine arts, it does, in fact. Okay, so moving on. Now you know how to play golf with a piano. The really funny thing is there's actually this guy in England. He actually owns a castle. He's a lord. I think he's Scotland actually. I think he's a Scottish laird, as they call them. They're spelled differently too. But he actually built a trebuchet large enough to throw pianos and cars with, and he does it. He actually threw a flaming piano across his estate. It was just, I'm like, man, if you got the money and you can do it, why not? It's just so cool. There's a great YouTube video of him throwing cars and pianos. A great many YouTube videos, actually. All right, so now we're going to get into the last section, which is the addition of velocities. We're going to learn our first thing about relativity. It's pretty straightforward. Here, here's an example. We have a boat traveling across a river, but because the river is moving and the boat is moving, there are two velocities to the boat. You have the boat, the rower rowing the boat in the y direction, and the river pushing the boat in the x direction. So you add those two things that are contributing to the velocity together to get the total velocity of the boat. It's pretty straightforward and simple. And it's just a simple vector addition. If the boat is moving at 5 meters per second this way, and the river is moving at 10 meters per second this way, then you use the Pythagorean theorem and you calculate the overall velocity of the boat this way, and then you use the inverse tangent to calculate the angle that the boat's moving, and you're done. Here's a slightly more complex example. You have a plane that is moving forward because of its propeller, but the wind is pushing it backwards at an angle. So the wind velocity is this one, the plane velocity is this one, but the overall plane velocity is actually this one. This is extremely important for boats and planes. They have to know not only how fast their propulsion system is pushing them forward, but they also have to know what the wind and the water or the water is doing to the boat so that they end up in the right place. So they end up going the right direction, right? If this plane is trying to fly straight north, then they're going to have to turn their plane slightly to the east to counteract this wind, right? So they're actually going to be sliding, like flying sideways through the air a little bit. And that happens all the time with airplanes. Otherwise, you end up in the wrong place. You gotta know these things. With GPS, it makes it a little bit easier nowadays, but it used to be that before you go up and fly a plane, you'd actually have to look at the wind charts for that particular time frame that you're flying. So if we were going to fly this afternoon, we'd look at the wind charts around North Platte, between North Platte and say Kearney or something if we're flying to Kearney. We'd look at the wind charts and we'd calculate all of our velocities based on those wind charts. So we'd know that, oh, we have a wind coming in from the north, so we need to fly slightly to the north at this particular angle to overcome that so that we can get to where we want to go. And it's not an exact science. It's always a little bit iffy. If you're in a bigger plane that has more advanced equipment on board, then it actually can measure the wind outside for you and other things like that. Or it has radar beacons that can communicate back and forth with different radar towers. Sometimes you just kind of have to call and figure out where you're at. That happens too. But in this case, you're adding these two vectors, and it's giving you the total vector of the plane going off here to the left and forward. Here they do this example with the boat on the river with two different velocities, calculate that final velocity. Pretty straightforward. They also do the one with the plane. Here they actually want you to calculate what the wind is. They tell you the velocity of the plane is 45 meters per second to the north. They tell you that the total velocity is 38 meters per second at this particular angle, and they actually ask you to calculate the velocity of the wind. So in that case, you either have to take the plane velocity and subtract the total velocity, or you have to do the math and do this velocity of plane plus velocity wind equals velocity total. And well, you're taking total velocity minus plane velocity. But you either have to do that, or you have to, and this is what they actually do. They actually write down the equation, total velocity equals wind velocity plus plane velocity, and then they solve that equation for the wind velocity. So when they solve that equation for the wind velocity, then they get wind velocity equals total velocity minus plane velocity. But they do it in Y direction and they do it in the X direction. They do it in both directions, and then they have to solve it both ways. So here they solve it in the Y direction. Here they solved it in the X direction. They get the actual answer. Here they solve it in the Y direction and get their answer. And then they calculate the total wind velocity by using the Pythagorean theorem to add them together. So this section of the chapter is not anything really new or different as far as mathematics go or the mechanics go of the science. It's just a different way of looking at it, from a kind of different point of view, but it's the same stuff. And that leads us to the idea of relativity. It really depends on, velocities, measurement of velocities, determination of velocity, and perception of velocity is actually relative to your point of view. It's similar to the beginning of last chapter when we talked about the man on the plane kind of thing, right? So it's even in 2 dimensions, it gets even more complicated. It's actually, there's an interesting situation you will encounter many times, probably without even noticing it, but you may notice it now that I'm going to tell you about it. When you're coming up to a stop sign, a 4-way stop sign, and somebody else is coming on the road that intersects yours, and you're coming and you watch, and if you're far away and you watch this person come up to the stop sign, you may notice that it doesn't look like they stop necessarily. It looks like they maybe just slow down and then start going again. And it very much looks that way, and the closer you get, it gets like there's this kind of sweet spot where it really is pronounced, where the person just looks like they just kind of roll through the stop sign. And as you get really close, you can tell because you can look at their wheels and you can actually see their wheels stop. But it's still not exactly, it's very difficult to see that motion that's 90 degrees to your motion while you're moving. Once you've stopped, then you can see it. But while you're moving towards them and they're moving across your path, it's difficult to tell because of the relative motions. And watch this while you're driving around. You'll see that it's true. It can be very kind of weird, especially if the person just stopped momentarily and then goes again. Well, a physicist was actually given a ticket for rolling through a stop sign when a police officer was coming up to the 4-way stop that way. And he argued his case in court using this very idea and demonstrated to them using a video. And he got out of his ticket for rolling through the stop sign. Even if he did roll through it, he got away with it. But there are many things like that, especially like pulling up to a stoplight, and then the stoplight turns green as you're stopping, and somebody next to you starts to go while you're stopping, right? That makes you feel really weird because you're not sure if you're stopping or they're going, or they're stopping and you're going. Whatever, you're just like, whoa, what's going on? It's kind of weird relative motion thing. So it can get kind of weird. It's particularly weird if you're rotating, if you're turning, right? You may have been inside of a, trying to think. Have you ever been in one of these carnival rides where you stand and you go inside this thing and it starts spinning and stand against the wall and the floor falls out? You ever been in one of those? Yeah, you've been in one of those. So if you ever go into one of those and you're like me and you do something that you're not supposed to do because they tell you you're not supposed to do, then you'll see some weird things. Like, for example, if you bring something in there to throw, if you bring something into there to throw, it won't go straight anymore. It will actually look like it's curving because it is going straight if you looked at it from outside the machine. But since you're not outside the machine and you're rotating, you throw it straight and then you rotate away from it. So it looks like it's rotating away from it. It looks like it's turning away from you. And you can actually hit the person next to you with popcorn, for example. Throw it out and hits them in the face. Excuse me. We had a rotating room in our physics department that helped us to understand those things. So call it the vomit mode, the vomit vortex, we called it, because a lot of people got sick. Anyway, that's it for today. That takes us all the way through section 3 and two-dimensional kinematics. And so we will answer any questions that you have on chapter 3 homework on Wednesday. And if we have time, we'll get started on chapter 4. We're in a good way. We're getting through stuff pretty quickly here. This is great. Have a great day. We'll see you Wednesday. If you're spinning fast enough, you could throw it and then get all the way around and catch it again. In which case, it would look like it was going away from you and looping around, like it looked like a boomerang kind of thing. All right.
There's a possibility. I'll
Okay.
shoot you an email too.
Yeah.
I might be able to cut the rooms. I'm gonna try to do that. But might not be able to get it. So.
Okay. Yeah, just shoot me a quick message and let's see, what am I doing here? Stop sharing. Gotta stop.